Welcome to another Mythology video. Ever heard of Ptolemy's theorem? It made a guest appearance in my last video. Incredibly important, incredibly beautiful, and an incredible crime that nobody tells kids about Ptolemy anymore. Let me quickly remind you what this super theorem is all about. Pick any cyclic quadrilateral, let's say quadrilateral with all its four vertices on a circle. Label two opposite sides, capital A and lowercase a, and the other two opposite sides, capital B and lowercase b. Next, let's call the diagonals capital C and lowercase c. Then A times A plus B times B equals C times C. That's Ptolemy's theorem. And of course, AA plus BB equals CC rings a very, very loud bell, right? Yes, of course, Pythagoras theorem. In fact, if our quadrilateral is a rectangle, then opposite sides are the same length and the diagonals are also the same length. And so Ptolemy's theorem morphs into a Pythagoras theorem. A squared plus B squared equals C squared. And just in case you are looking for a right angle triangle, well, here it is, half the rectangle. This means that Pythagoras' theorem is a special case of Ptolemy's theorem. Ptolemy beats Pythagoras. All right, my mission today is twofold. First, after watching the last Mythology video, mathematician Rainer Lang sent me his visual proof of Ptolemy's theorem. In my opinion, Rainer's new proof is the simplest and most powerful visual proof out of all the many proofs that people have found in the 2000-year history of this mathematical gem. Really quite amazing that this one seems to have fallen through the cracks. My main mission today is to let the world know about Rainer's amazing proof. My other mission is to tell you why Ptolemy's theorem is so important, beautiful and fun, and why it is really a crime not to tell kids about it in school. To set the scene, let's have a look at one of the most important books in the history of science, the Almagest. The Almagest is a 2nd century astronomical treatise by Claudius Ptolemy that systematically presents the geocentric model of the universe. That is, that the Earth is the center of life, the universe and everything. For over 1,000 years, the Almagest remained the authoritative reference for astronomical knowledge and calculations in both the Western and Islamic worlds. Just think about it. A book in print and used for over 1,000 years. Mind-boggling, isn't it? Now, in this 400+ page Latin edition of the book over there, the text where Ptolemy states and proves his theorem ends up right at the beginning, on page 10. After he proves his theorem, Ptolemy uses it to calculate a table of chords, which is equivalent to a 5-place table of sines from 0 to 90 degrees, at intervals of quarter degrees. For example, that entry there translates into the fact that the sine of 1 degree is approximately 0.01745. Let that sink in. 2,000 years ago, they knew that the sine of 1 degree is 0.01745. Pretty amazing, isn't it? It took over 1,500 years for people to produce something substantially better. And so all this is a really, really big deal. And Ptolemy's theorem is at the heart of it. In fact, knowing what Ptolemy knew, you can do pretty much everything that you can do with modern trigonometry. Anyway, I just thought it would be good to hammer right from the beginning how big a deal Ptolemy is and what a scandal it is that most of you will never have heard about any of this in school or anywhere else. Now, bit of a challenge for you. In the next 2 sections, I'll be lying a tiny little bit here and there. Of course, I'll be lying for goodness and not evil. And I'll also come clean in the last chapter, but see whether you can catch my little lies before I confess to them and make amends. Okay, let's warm up with 2 other gems from classical geometry, which we'll also need to be familiar with later on. All right, first fact. In a cyclic quadrilateral like the one over there, opposite angles add to 180 degrees. Always. Did you know that? There, those 2 angles, they add to 180 degrees. Same for the other pair of opposite angles. Looks convincing, at least in the case of this particular cyclic quadrilateral. But why is this always the case? Why do opposite angles in a cyclic quadrilateral always add to 180 degrees? Let me show you how you can see this at a glance. There, that's the center of the circle, and that's a radius. And here's another radius. This means that this triangle there is an isosceles triangle, and that means that these two angles are the same. Same here, and here, and here. Great. 4 different angles, red, green, blue, brown, 2 copies each. Now, let's have a closer look at those pairs of opposite angles and highlight the 4 colored angles within them. And so, the angle sum for this pair is the sum of red and blue and green and brown. But the same is the case for the other pair of opposite angles. The 2 angle sums are the same. They're the same. And so, the sum of opposite angles is half the sum of all the angles in the quadrilateral. But then, just like in a rectangle, the sum of all the angles in a quadrilateral is 360 degrees. And half that is 180 degrees. Opposite angles add to 180 degrees. How pretty a proof is that? In fact, a quadrilateral is cyclic exactly if this is the case. Remember this fact for later. Now, here's the second gem. Start with any chord of the circle. Then all the angles on one side of the chord are the same. Quite surprising the first time you see this. But that's not all. If this is the center of the circle, then this angle in the middle is exactly double the purple special angle. And how do you see that this is always true? Also easy. Put in another radius and highlight these angles. Then obviously the 3 angles add to 360 degrees. But we can also get 360 degrees in a second way. There. You all know that the angles in a triangle add to 180 degrees, right? And here we have 2 triangles, and so 180 times 2 is another 360 degrees. There, 180 once and twice. Subtract the green and orange on both sides of the equation and watch the magic unfold. Ta-da! The angle in the middle is 2 times the purple angle. Very, very pretty. And of course, there was nothing special about this particular purple angle, and so we conclude that all the purple angles are equal to half the angle in the middle. Great! Now, a particularly interesting special case arises when the chord we start with is the diameter of the circle. In this case, the angle in the middle is 180 degrees, and so in this case, the special angle is half of 180 degrees, 90 degrees. This special case is also known as Thales theorem, super famous. Having fun so far? Some of this may already be familiar to you from school geometry, or at least was familiar to you once upon a time. But hopefully I've made it a little prettier and more memorable. All right. Let's start with a couple of nice applications of Ptolemy's theorem. We already stumbled across one super application right at the start, Pythagoras theorem. What else is there? Well, Ptolemy says cyclic quadrilateral implies AA plus BB equals CC. What about the other way around? What about the converse of Ptolemy's theorem, right? Start with 4 points in the plane, calculate all the distances between these points. Now, calculate the sum of the products of opposite sides, as well as the product of the diagonals. Now, let's say these 2 numbers are equal, as they really are in this case. Does this imply that the 4 points are in a circle? Well, turns out this is really the case. AA plus BB equals CC implies that our 4 points form a cyclic quadrilateral. Great! So, next time your life depends on deciding whether 4 points are in a circle, you know what to do. Next application. Ptolemy's theorem is a great tool for exploring regular polygons. Why is that? Well, because all the vertices of a regular polygon are contained in a circle. You can then focus on quadrilaterals that share those vertices to mine for information about the polygon and its diagonals. I did something like this for the heptagon over there in the last video. Here again is one example that we looked at then, but with a nice twist. Okay, in a regular heptagon there are 2 different types of diagonals. Now, Let's single out a quadrilateral that shares 4 of the vertices, this one here. It's full of those diagonals and sides of the heptagon. Now let's unleash Ptolemy. Q times R plus Q times S equals S times R. Divide by the product of all 3 lengths and go for a cancelling spree. A very interesting identity, isn't it? The reciprocals of the 2 diagonals add to the reciprocal of the side. Now, to appreciate how nifty a tool Ptolemy's theorem really is, try to prove this identity without Ptolemy. Share the tales of your struggles in the comments. Now, let's also quickly go on a little bit of a tangent here. Among other things, our diagonals and sides being related like this means that if you do this strange thing, then the red side fits nicely in like this. Check out the wiki page for the so-called optic equation for this and more fun facts about this interesting relationship up there. In any case, if you're interested in maths competitions, definitely make sure to add Ptolemy's theorem to your repertoire. Pops up all the time. All right. The last application that I'd like to highlight today already appears in the Almagest, immediately after the proof of Ptolemy's theorem. This one is a really big deal. Let me describe this application in modern language. Let's start with one of the diagonals and extend it to a triangle like this. What's the angle at the top again? Remember? Yes, this is the right angle. At another triangle at the bottom, another right angle. Okay, what we are now also looking at is a special cyclic quadrilateral. Let's see what Ptolemy pans out to be for this quadrilateral. Turns out that the lengths of all sides and diagonals of this quadrilateral can be expressed in terms of these 2 angles, alpha and beta, and in terms of the diameter, which we'll choose to be 1 unit long. Okay, first these 2 sides. What are they? Easy. Dust of the trigonometry cobwebs. Obvious, right? That's sine alpha on the right and cos alpha at the bottom. Cool. What about the remaining 2 sides? Well, same thing. Sine beta and cos beta. And so there's only this one diagonal remaining to be puzzled out. Not clear what that is at the moment, so let's call it M for mysterious. Okay, let's intone Ptolemy for this quadrilateral. The product of the diagonals, M times 1, that's M, is equal to the product of these 2 opposite sides, okay, plus the product of the other 2 opposite sides. Who can guess where I am going with this? I'm sure all trick demons among you will have a very good guess. Well, guessing or not, let's now figure out what M is. For this, let's first zap all the stuff that we don't need anymore. Does this ring a bell? No? Well, the angle at the top is half this angle. Remember now? Our second gem from the warm-up. All right, so half that angle in the middle is also alpha plus beta. Almost there. Again, let's zap all the bits that we don't need anymore. Okay, now the diameter was 1 unit long, and so the radius is half a unit long. All right, just another sine thingo. Half the red distance is just the sine of alpha plus beta times 1/2. And so the whole red distance is 2 times that. Fantastic, don't you think? So our special type of quadrilateral translates into the super famous sum rule for sine. What's also super nifty is that we get the difference rule by simply flipping the triangle at the bottom up to the top. Ptolemy is so cool, don't you think? The sum and difference formulas for the cosine look very similar. In addition to all this, Ptolemy also derived these half-angle formulas. And then starting with some no-brainer sine and cosine values corresponding to basic angles like 60 degrees and 90 degrees, and using these formulas, Ptolemy was able to construct his accurate trigonometric table. Very impressive, isn't it? Definitely check out the wiki page on Ptolemy's theorem for a lot more nice applications of everybody's new favorite geometrical gem. That was great fun, but it's now time to get down to work and show you Rainer's fabulous proof. That's Rainer over there. What do I know about Rainer? Not much, apart from the fact that he's from Berlin, that he studied maths at uni, and that he has more hair than me. All right, here we go. There's actually a bit more to Ptolemy's theorem than what I've told you so far. Obviously, not all quadrilaterals have their vertices contained in a circle. For example, the vertices of this quadrilateral here are not all contained in a circle. There's only the one circle over there that contains all three yellow vertices, and then the red vertex is not where it needs to be. But it turns out that given any quadrilateral, we always have AA plus BB is greater than or equal to CC. And we get equality if the four vertices are on a circle. This result is called Ptolemy's inequality, sort of the bigger brother of Ptolemy's theorem. What Rainer does is to prove Ptolemy's inequality in an extremely visual way. Here's what he does. He starts with a quadrilateral, makes three copies, scales the three copies by lowercase a, b, and c. There, everything times a, everything times b, times c. We only need a few of those lengths, and so let's zap the rest. Now there, at the bottom, we've got the three ingredients of Ptolemy's inequality, AA, BB, and CC. That looks promising. What about the rest? Well, there are three pairs of equal lengths that will allow us to line up our three quadrilaterals in a nifty way. Have a look. There. Those two sides are the same, and so we can align the first two quadrilaterals like this. Cute. Second pair. Those two red lengths are also the same, as are these two green ones. And then the angles between the red and the green segments also look the same, don't they? And they really are the same, because the two smaller angles these purple angles are made up of are the same. Here, this smaller angle is the same as the small angle over there. Can you see it? Okay, and this small angle is the same as that one. Great. And that means that we get a perfect fit like this. And now, did you already have a big aha moment? No, not yet. What about now? AA plus BB at the top of the orange triangle is greater than CC at the bottom. Ptolemy's inequality at a glance. How nice is that? And that's always going to be true no matter what quadrilateral you start with. Always greater, except when? Well, except if this point ends up on CC, right? If this point ends up on CC, then AA plus BB equals CC. And when does the point end up on CC? Also easy. The point ends up on CC if these two angles add up to 180 degrees. But since in a quadrangle, the green angle is the angle opposite the red angle, our very first geometrical warm-up gem strikes. The geometrical gem about opposite angles in a cyclic quadrilateral adding to 180 degrees. And so we conclude that if our quadrilateral is a cyclic quadrilateral, we get equality. Beautiful proof, isn't it? To summarize, make three copies, scale by lowercase a, b, c, and line up. Then AA, BB, and CC form a triangle, and our inequality follows. Except it doesn't. Always. I'm sure you've all been waiting for me to confess to some lies. How did you go with the lie detection? Well, here it comes. Often in classical geometry, when people present proofs by referring to some diagrams, those proofs are incomplete. Looks really can deceive. For example, remember this diagram here? There, flicking back and forth, you can see at a glance that the two sums of opposite angles are the same. Clear? There. However, strictly speaking, my proof only works without modification if the center of the circle is contained in the interior of the quadrilateral. Right? But there are also cyclic quadrilaterals where this is not the case, like this one here. In a quadrilateral like this, the angle on the left is no longer split into two smaller angles as before, and so our flicking proof does not work anymore, at least not without some modifications. Bummer! Now, very important, even in this mucked up case, sums of pairs of opposite angles are always equal to 180 degrees. It's just that the proof I showed you does not straight away cover this mucked up case. But this can be fixed. If you can see how my proof can be modified to also give a proof for this special case, please dazzle the rest of us with your proof in the comments. More lies. The diagram I used for the second proof in the warm-up, that one there, also does not cover all possible cases without modification. Anyway, you won't be shocked to hear that I'm not the only little liar in Mathsland. Many other diagram-based proofs in geometry textbooks really only work in special cases, but this fact is, more often than not, glossed over. And such is also the case for Reiner's proof. At least to start with, it really only works for a special kind of quadrilateral. It only works for convex quadrilaterals. That is, quadrilaterals in which the diagonals are contained in the interior of the quadrilateral like this. So it works for the sort of standard quadrilaterals that most people associate with the word quadrilateral. However, Ptolemy's inequality works for all quadrilaterals. So also for the ones that have an indentation, or the ones that cross themselves, or even degenerate ones like this one here. In fact, it even works for warped quadrilaterals that snake around in 3D space. And so, given the abundance of special cases, it looks like we are not even close to a full proof of Ptolemy's inequality. However, it turns out that what Reiner sent me can be easily extended into a full proof, and you can literally see that extension by blinking your eyes. How come? Well, have a look at the picture over there. See that green triangular pyramid around which our 3D quadrilateral winds? Interesting, huh? And I didn't just put that in to highlight that we're dealing with a true 3D quadrilateral. Okay, have another look at this picture. On the count of 3, blink your eyes. 1, 2, blink! Now, don't these quadrilaterals all of a sudden look like triangular pyramids? Aha! And so shouldn't Reiner's proof also work if we are dealing with a real 3D quadrilateral? And that's really the case. I'll present detailed animations of the 2D and 3D versions of Reiner's proof at the end of this video. In particular, what the 3D version of the proof will show is that for a true 3D quadrilateral, so one that does not fit into a plane, the AABBCC triangle is always a real triangle, unlike for a flat quadrilateral, that AABBCC triangle can never degenerate into a straight segment. And so that means that for true 3D quadrilaterals, AA plus BB is strictly greater than CC. And here comes the greatest thing about all this. The strictly greater inequality for true 3D quadrilaterals implies the greater or equal inequality for absolutely all quadrilaterals, no matter how weird. Why, you ask? Well, take for example the blue quadrilateral. We're interested in comparing AA plus BB and CC. Now what you do is to grab one of the vertices, say the one at the bottom, and push it out of the plane it's sitting in at the moment into 3D, just a little bit. This means that now we're dealing with a true 3D quadrilateral, and we can therefore be sure that the question mark is a greater sign. Now let's slowly move that bottom vertex back to its starting position. Until the very last moment of this movement, we're dealing with a true 3D quadrilateral, and therefore we have a greater sign. And so this means that at the last moment, when the quadrilateral returns to being a flat quadrilateral, the greater sign either stays a greater sign or it becomes an equal sign. And so what the true 3D version of Reiner's proof shows is that for absolutely every quadrilateral, AA plus BB is greater or equal to CC, and that we can only possibly have equality if we're dealing with a 2D quadrilateral. That's a pretty nifty argument, don't you think? And a little bit more mucking around shows that among all the 2D quadrilaterals, it's precisely the cyclic ones that make Ptolemy go equal. Now, just to make sure that you don't get the wrong idea here, when people say cyclic quadrilateral, they really mean cyclic and convex, like the one over there. Just because the vertices of a quadrilateral are all contained in a circle does not make it cyclic. For example, this quadrilateral over there is not cyclic, and we also don't get equality. Also, for everything I said to work, you always have to make sure that the lower and uppercase a's really are opposite sides, and the same for the lower and uppercase b's. Or equivalently, you have to make sure that as you travel around the quadrilateral, the a's and b's have to alternate. A, B, A, B. There A, B, A, B. Anyway, I think by now 99% of you who've made it up to here would be very happy accepting that Ptolemy's theorem really holds, and will be also very happy to leave the movie theater once the final animation has finished. For the remaining 1%, I'm going to do a Marvel movie stunt and include an Easter egg after the credits. Alright, as promised, to finish off, here's a little animated exploration of Reiner's proof in which I highlight some patterns, some special 2D cases, and a 3D extension. Enjoy! Here's the promised Easter egg for all of you diehards. I mentioned degenerate quadrilaterals a few times, but did not dwell on them. Degenerate quadrilaterals can be triangles with an extra vertex along one of the sides, or even with one corner playing the role of two vertices. Or even more extreme, a quadrilateral can degenerate into a line segment, or even a single point. Here are two footnotes about degenerate quadrilaterals. Footnote number 1. For some of these super degenerate quadrilaterals, like the one over there, just displacing one of the vertices into 3D may not be enough to make them into true 3D quadrilaterals. And so my argument showing that Ptolemy's inequality is always true also needs a minor fix to make it work for super degenerate quadrilaterals. Easy enough. Instead of just one vertex, displace a couple of them to form a true 3D quadrilateral and then move them back simultaneously to their original position to see in exactly the same way as before that we always have greater or equal, even for these degenerate cases. For the second footnote, I've prepared another nice animation for you. Have a look. And so the second footnote just says that apart from cyclic quadrilaterals, there are also some super degenerate linear quadrilaterals in which Ptolemy's inequality is an equality. And as a footnote to this footnote, let me also mention that, as with circles, it's not enough for our vertices to be contained in a line to guarantee equality. The A's and B's also have to cycle around the segment as in this example. Alright, now we really dotted most of the I's and crossed most of the T's, and only some innocent mini lies remain. And so let's call it a day. Until next time.